Moving on from our series of lectures on the cardiovascular system, blood, now going to move on to actually do the heart and its anatomy fully. The basic things we need to go over in this are basic anatomy and the circulation of blood through the heart, the cardiac cycle in terms of the mechanical events and the electrical events. You will be doing a practical on the electrical events of the ECG, so for the moment try and get to grips with the details, ready for the practical. Mentioned previously, so just a quick reminder that we have a cardiovascular system because we have an oxidative metabolism. We need oxygen in order to create energy with our mitochondria, and therefore we have the limits of diffusion to deal with. If we relied on diffusion on its own, it would take far too long for oxygen to actually get into our cells. As a result, we need to have an oxygen transport mechanism. We've already discussed oxygen transport from the air to the blood by diffusion. So now we're going to start discussing about how that blood gets around the body. Hopefully you're all aware of where your heart is located. This diagram shows you the structures that you have present in your thoracic cavity. Starting at the top, there's the thymus gland coming down into the chest cavity itself. The large blue vessel you can see on there is your vena cava. The large red vessel is the aorta. The arch of the aorta is identified on the diagram along with the pulmonary trunk. The lungs are shown. On top of the lungs you have a pleural membrane which protects the lung, prevents friction between the lungs and the muscles of the rib cage. The heart is located in between the two lungs itself. We refer to the base of the heart as being the apex. It's the pointed section which always points down and to the left on the body. The diaphragm is the thick and solid sheet of muscle that separates your thoracic cavity from your abdominal cavity and therefore keeps the organs separate. You need to be aware of the structure of the heart, of the characteristics of each part of the heart itself, each of the chambers, and the direction of blood flow. So, start at the right atrium. Remember when you look at a diagram of a heart on the screen, it will be in reverse, so it'll be as if I was standing in front talking to you. So the right atrium receives venous blood, so venous return from the superior and inferior vena cava. Blood passes from the right atrium into the right ventricle through the tricuspid valve. Remember from before I've said I'm quite happy for you to just call it the right atrioventricular valve. It's called the tricuspid because there are three pieces of tissue that make up this valve. Once in the right ventricle, blood exits into the pulmonary artery via the pulmonary valve. Blood is then pumped into the lungs where it receives oxygen and releases carbon dioxide. On return back, the blood comes back into the left atrium via the pulmonary vein. The blood passes then from the left atrium through the mitral valve, is the left atrioventricular valve, also called the bicuspid valve, into the left ventricle. It's bicuspid because it has two pieces of tissue. Once in the left ventricle, the blood will then pass from the ventricle into the aorta via the aortic valve, and his blood is then pumped to the body through the arteries and the rest of the vascular network. When we look at the heart itself, so here what we've effectively done is sliced straight through, so we've almost removed the atria and we're looking directly at what is happening within the ventricles of the heart, between the ventricles and the atria. So these are the heart valves. The top you can see is the pulmonary valve. These are called semilunar valves. They have formed these cups of tissue, so as blood backflows down to try and get back into the ventricles, it fills these pouches and they snap shut. The outside of this is called the pulmonary fibrous ring. You do not need to worry about the full anatomical terms that are used on these diagrams, but I do need you to understand the structures and where they're placed. Below the pulmonary vessel, you'll see the aortic vessel. So there's the aorta itself, and again you have the semilunar valves present. On this side you can actually also see the coronary arteries. Below the aorta, on the left, you see the bicuspid valve going into the left ventricle, and on the right, the tricuspid valve going into the right ventricle. As you can see, it's quite clear why they're called bicuspid and tricuspid valves, by the number of pieces of tissue. Circulation itself, you have two forms of circulation. First of all, I want us to focus on the blood circulation. So the heart is shown in the centre, deoxygenated blood is shown in blue, oxygenated blood is shown in red. So first of all, the blood flows through the right atrium to the right ventricle, then up to the pulmonary circulation. This is called the pulmonary circuit, and it's where the blood passes through the blood vessels and capillaries in the lungs, the pulmonary capillaries, to receive oxygen. That oxygenated blood is then returned to the left side of the heart, where it's then pumped around via the aorta and the arteries into the systemic circulation. So this is called the systemic circuit. You'll note on both of these that you have a green circulation as well. The green circulation is your lymphatic circulation, which we'll come on to a bit later. The key thing here that I need you to understand is that the lymphatic circulation runs in parallel to your blood circulation. So you have lymphatic capillaries passing into lymph nodes, you have valves along the lines of the lymphatic vessels similar to the veins, and you have a lymphatic duct which allows the lymph fluid to pass back into the vena cava before it's taken off to the heart. So when we look at the heartbeat, we're referring to one entire cycle, the heart's atria filling, the ventricles filling, and the blood being ejected. So if you start at the left-hand side diagram first of all, here we're showing you where the right ventricle, left ventricle, and the vessels are. So initially blood flows into both of the atria. As blood flows into the atria, everything relaxes, the heart is relaxing at this point, so the blood is flowing down into the ventricles. As we move down to the bottom diagram, at this point the ventricles are contracting. As the ventricles are contracting, that forces the atrioventricular valves closed, so blood cannot flow back into the atria. Once the vessels have relaxed, the heart is relaxed again, once again blood can flow into the heart, through the atria and back into the ventricles. And this cycle repeats. When we talk about the cardiac cycle, we're referring to the electrical events of the heartbeat as well as the mechanical events. This is quite a heavy diagram, so I want to describe it for you in sections, starting at the bottom. So the bottom shows us the phases of the cardiac cycle. In the first diagram, you can see atrial contraction occurring. So that's when the atria are starting to increase in pressure, they're contracting, they're forcing the blood down into the ventricles. The second stage is termed an isovolumetric contraction. At this point, the ventricle is starting to contract, the bicuspid and tricuspid valves, those atrioventricular valves, have closed. However, the pressure is not yet enough to overcome the resistance of the semilunar valves in the pulmonary trunk and the aorta. So at this point, although the heart is contracting, the volume remains the same. The second phase is ventricular ejection. At this point, the pressure in the ventricles has now increased. It's overcome the resistance of the valves in the aorta and the pulmonary trunk, and blood is ejected out of the heart, either to the lungs from the right side or the body from the left. The fourth phase is termed isovolumetric relaxation. At this point, the heart is starting to relax, blood is flowing into the atria, but it hasn't flowed enough to overcome the resistance of those atrioventricular valves. So again, at this point, the heart's volume remains the same. Next is ventricular filling, which again is where there's enough blood now going through into the atria. It's pushing open the atrioventricular valves and starting to fill the ventricles. And finally, we're back at the stage where we have atrial contraction at stage 1. So that's what's happening mechanically in the heart. You also need to understand what's happening with the pressures in millimetres of mercury occurring during this cycle. So first of all, atrial contraction. If you follow that line up into the diagram, you'll see as the atria are starting to contract, you're starting to see an increase in left ventricular pressure and left atrial pressure. You would expect that. You're also seeing that the aortic pressure, which is the red line on the curve, is actually slowly decreasing. It stays fairly constant at this point. In the second stage, the isovolumetric contraction, if you follow that up to the graph, you'll see a very narrow band on the graph. What you're seeing here is the bicuspid valve is closing and you see a dramatic increase in pressure in the left atria and also the left ventricle. As that increases, you reach a point, if you see on the diagram it says point 6, aortic valve opens. At that point is where the pressure has reached the stage where it can now actually open the aortic valve and blood can be ejected. That brings us on to the ventricular ejection. As you look at ventricular ejection, you'll see that the green line showing left atrial pressure drops dramatically. During this phase it does increase very slightly, but not a lot. However, the left ventricular pressure and the aortic pressure are at their maximum. This is the point that we term ventricular systole. So this is the point where the ventricles are actually contracting hard. The previous point, where we had the increase in pressure in the left atria and the left ventricle, is termed the atrial systole. So the point at which the atria are contracting. If you go back down to the bottom line of the diagrams to where it says isovolumetric relaxation, the fourth diagram along. If you look up to the pressure graph, you can see again during this phase there's a gentle increase in the left atrial pressure. At the end of this phase, the bicuspid valve opens because you've reached enough pressure from the atria filling with blood to overcome that resistance. The left ventricular pressure drops very rapidly in this phase. The aortic pressure is slightly unusual. At the start of the isovolumetric contraction, the aortic valve closes. You would expect to see a dramatic drop. If you remember from the last lecture when we did hemodynamics and how we calculate for mean arterial pressure, cardiac output, etc., you remember that the pressure over time curve showed an increase in pressure and then another little increase. This is called the dicrotic wave. You don't need to worry at the moment about why that happens, just be aware that it's there. As you move into the ventricular filling stage, you'll see that the pressure in the left atria and the left ventricle is pretty much the same. It's very low. The aortic pressure is dropping, but gradually. That's because of the major elastic components of the aorta. It means that the aorta has expanded and is now recoiled, so there's still considerable aortic pressure. This phase, so the isovolumetric relaxation and ventricular filling, corresponds to the relaxation period in the heart. So this is the point at which blood will flow into the coronary blood vessels itself. At that point, we're back to the beginning with the atrial contraction. Now if you look at the very top of this diagram, you will see the ECG trace. This is a very much simplified ECG trace. You need to know what each of those waves and points corresponds to in terms of the actual contraction of the heart. So first of all, the P wave itself actually begins in the ventricular filling stage. The P wave starts to increase as the ventricles are filling. During atrial contraction, we see halfway across the P wave and includes the Q to R part of it. The QR complex bridges the atrial contraction and the isovolumetric contraction. As we move into the ventricular ejection, you see on this graph it's 0.8, it's the T wave. The T wave is slightly behind that massive increase in pressure of the aorta. As you move to the isovolumetric relaxation, by the end of that point it's the end of the T wave, and then you have a flat line on the ECG which indicates when the heart is actually relaxing and the ventricles are refilling. I will need you to understand what is happening with the electrical events going on in the heart and what the P, QRS and T parts of the ECG actually relate to in terms of repolarization of the various parts of the heart. So, for cardiac muscle, I need you to review muscle contraction. Have a read in your textbook on muscle contraction to remind yourself of the sliding filament hypothesis. Remember that the interior of the myofibril contains a special type of endoplasmic reticulum which is called the sarcoplasmic reticulum. This is our intracellular calcium reservoir. The myofibril, like other muscle cells, still contains an array of actin and myosin filaments which slide along one another to achieve contraction, and this is the sliding filament hypothesis. If we look at cardiac muscle itself, you'll see that structurally it looks very different to the striated muscle of, say, your skeletal muscle. We will cover muscle contraction soon. The key thing I need you to know here is that calcium is the crucial ion involved. In the cardiac muscle fibres, each of these fibres is separated by intercalated discs to each other. If you have a look on this diagram, if we start at the top, we have desmosomes, which are acting to hold those fibres together. There's a huge amount of mitochondria in the fibres to provide the energy they need for contraction. The sarcolemma, the outer membrane, the nucleus is shown in this diagram as these large purple shapes. So each fibre is intercalated discs between the fibres. There are also gap junctions involved. So you've got a very complicated array of various cell adhesion molecules holding each one of those fibres together so that the muscle can contract as one piece. Cardiac muscle has an unusual length-tension relationship in that increases in the initial muscle fibre length, termed the preload, lead to an increase in the active tension that we can generate. When we talk about preload, we refer to the initial stretching of the cardiac myocyte prior to contraction, related to sarcomere length. If you remember that in the heart, you have these isovolumetric contractions, isovolumetric relaxations. So as the heart is filling, those cardiac myocytes are being stretched very slightly. Ionotropy is a measure of contractility, so how much those cells will contract for a given preload. We can alter the ionotropy with drugs and with hormones. Effectively, what this means is that we can change the amount of force that the heart fibres generate at a particular fibre length, so the heart can respond to demand for more blood or less blood, regardless of what else is happening in the body. All of this relates to something called Starling's law of the heart, and you must know this. Starling's law of the heart dictates that the ventricular diastolic end volume, i.e. the amount of blood present in the ventricles at the end of diastole, is controlled by three things: ventricular filling pressure, central venous pressure, and venous return. In other words, the pressure of the blood coming into the heart and how much blood itself is coming into the heart. That makes sense. If you look at the diagram, we've got stroke volume in millilitres over ventricular end diastolic volume. For any given increase in stroke volume, you would expect to see an increase in ventricular end diastolic volume. The resting value is shown there, and it's probably around about the 120. The heart will change its force of contractility to deal with changes in ventricular diastolic end volume. So if we're doing a lot of exercise, for example, that will increase the ventricular filling pressure and the central venous pressure. It will also increase the venous return. As a result, that means that our ventricular diastolic end volume will increase. That means there is more blood in the heart, so the heart is stretched. That increase in stretch and increase in contractility means the heart can then pump a larger amount of blood out as its stroke volume to deal with increased demand. The heart itself beats continuously as a virtue of having an inherent rhythmical electrical activity. That activity is maintained even if the heart is physically removed from the body and all connections are severed. The cardiac muscle cells form two networks, one in the atrial network and one the ventricular network. You will all have heard of these cells, although you may not have heard the terms, but there are specialist myocytes present which create this autorhythmic behaviour. These are called the pacemaker cells. They contract the network of normal cardiac myocells via a conduction system. So you have a set group of cells in the heart that basically initiates the cardiac cycle and the beat of the heart. The pacemaker itself, if you look at this diagram of the heart showing the frontal section, this point, if you look in the right atrium, you'll see two dark dots. The first is called the sinoatrial node. This is a network that goes through both atria of the heart. So it not only projects the activity through the left atrium and the right atrium, but also links in with something called the atrioventricular node. This is located at the lower part of the right atrium. At this point, this node sends electrical signals through the middle of the heart through the septum. You need to know this conduction system. So from the atrioventricular node, we then have the atrioventricular bundle. This is also called the bundle of His and passes into the septum. That bundle separates and splits into left and right bundles and branches. As it gets down to the apex, those branches then veer off through the left and right cell walls, muscle walls of the heart, and those fibres coming off, in smaller amounts, are called Purkinje fibres. The electrical impulse begins in the right atrium, and it crosses across to the left atrium to instruct the atrial cells to contract. Meanwhile, the signal is sent via the atrioventricular node through the bundle of His, the bundle branches, and the Purkinje fibres to tell the ventricles to contract. As a result of this, there is a delay between atria contracting and the ventricles contracting. The pacemaker is located in two nodes. The first is the sinoatrial node. This is located in the right atria near the entry of the vena cava and paces the atrial network. The atrioventricular node lies at the lower end of the atrial septum, and as I said before, this signal propagates from the sinoatrial node to the atrioventricular node, the bundle of His, bundle branches, finally to the Purkinje fibres, and that paces the ventricular network. If you look at the diagram, this shows membrane potential against time in seconds. So you can see that we have, instead of having just a normal action potential, we actually have something called the pacemaker potential. These cells are naturally changing their own membrane potential. They are steadily depolarising. Once they reach a threshold level, at that point they spark an action potential. It then goes below threshold again, and once again we see this pacemaker potential bringing the membrane potential up to reach the threshold, and again the action potential. That is how these pacemaker cells actually govern the heart rate. We need to understand what is happening in terms of the electrophysiology in these cells. So in this diagram, we have membrane potential in millivolts against time, shown in this case 0.3 seconds, which is the approximate length of time it takes. So first point, you see a rapid depolarisation due to sodium inflow when the voltage-gated fast sodium channels rapidly open. So that first stage is a depolarisation stage. You then have a plateau, which is a maintained level of depolarisation. This is because you have calcium flowing in when voltage-gated calcium channels are opening. You're also getting some potassium channels starting to open, so you are getting some potassium outflow from these cells. However, the net result is that you maintain this depolarisation. Once you've reached probably around about 0.25 seconds, you reach the repolarisation stage, and this is due to closure of calcium channels. The potassium outflow is still continuing, and we're starting to add in voltage-gated potassium channels, so this allows a more rapid repolarisation to take our membrane potential back down to what it should be. If you look underneath the diagram, you'll find that the point from rapid depolarisation and up to where the repolarisation starts, all that section is depolarisation of the membrane. We refer to this as the refractory period, and it's happening pretty much from the start of depolarisation to where you're almost reached the normal membrane potential. That means that this refractory period, that particular cell cannot fire again until it's fully recovered. And the time we see contraction of the cells is actually the points where you have the plateau. So it's between where you have the rapid depolarisation and the rapid repolarisation. I told you we need to know more about the ECG, and as promised you will have a practical on this later on. So here we're showing two lines above the ECG. The blue shows atrial contraction, yellow shows ventricular contraction. We can use these intervals as being diagnostic. So for example, we have the P to Q interval is when we're starting to have contraction of the atria. The QRS complex, the ST segment, and up to almost halfway through the T wave is when we're seeing ventricular contraction. The two intervals that are most useful in diagnostics are the P to Q interval and the Q to T interval. So the P to Q interval is the point where the atria are contracting and may be delayed by scar tissue. Q to T interval is when the ventricles are starting to contract and when they're then relaxing and repolarising. And this particular interval is lengthened if you have myocardial damage from, say, previous heart attacks, coronary ischemia, or conduction abnormalities. There are conditions where the electrical conduction through the heart is affected, and these are known as blocks. Reading the ECG is a skill that you need to develop. So first of all, we start at the top of the diagram. Number 1, we have depolarisation of the atrial fibres produces the P wave. So the P wave indicates an action potential in the sinoatrial node. Once the P wave has come up, we then have atrial systole and contraction, and that is the end of the P wave before we reach the QRS complex. Depolarisation of the ventricular fibres produces the QRS complex itself, and ventricular systole, so ventricular contraction, happens at the end of the QRS complex, so the S to T interval. Repolarisation of the ventricular contractile fibres begins to produce the T wave. And finally, once the ventricle diastole occurs and the ventricles are relaxing, we see an end to the T wave prior to the beginning of the next ECG cycle. You must be able to identify the polarisation status, so depolarisation or repolarisation, of each part of the heart in relation to what is happening on the ECG. This is something we will do practice questions on, but together with the practical, hopefully you should be able to understand this quite easily. Here showing several different ECGs. The first at the top is a normal electrocardiogram. So at this point we're looking at the R to R interval. So you start off, you have the P to R interval, then you have QRS complex followed by the T wave, then a rest period, and then the repeat ECG. So we now have 4 heartbeats shown on this normal ECG. If we look at B on the left first of all, we have something called a first degree atrioventricular block. This means that there is a delay in the electrical conduction going from the atria to the ventricles. And in this case we see a prolonged P to R interval. So this is the point between, if you look at the last slide, between when we have the atria starting to depolarise and the ventricles starting to go. In section C, this is atrial fibrillation. So this is where the atria are not contracting rhythmically as they should be. At that point, what we see is no detectable P wave. The R to R interval is very irregular here. Because the atria are not contracting as they should be, there's no regulation to the heartbeat, and there's problems getting the ventricles to contract at the same times. At the bottom, we have 2 particularly severe ECGs. The first is ventricular tachycardia. Tachycardia means fast heartbeat. Bradycardia is slow heartbeat. In this case, this person is extremely ill indeed, and the ventricles are beating very rapidly and completely out of synchronicity with the atria. Ultimately, that can lead to a ventricular fibrillation, where the ventricles literally contract rapidly but not firmly enough to actually eject the blood. If you see on TV where they've got defibrillators, the electric plates they put on over the skin to shock the heart, this is the sort of situation that they would be trying to rectify. What they're trying to do is shock the heart electrically to effectively reset the pacemaker cells. If we look at a ventricular muscle cell, and this is the same diagram from before of membrane potential over time. So you can see first you have the rapid depolarisation, then the plateau period, and then a gradual repolarisation. The refractory period, as you say, is that point between the depolarisation and when the membrane potential has reached almost its normal level. There is always a slight overshoot in the membrane potential. The tension is developed during this refractory period, so that is the point when the muscles are contracting. So how do we coordinate contraction of the ventricles and the atria? In order for the heart to pump efficiently, we require atrial contraction followed rapidly by ventricular contraction. The heartbeat is controlled by our pacemaker cells and by non-contractile muscle tissue. This allows us to have an intrinsic and rhythmic generation of the action potentials. The sinoatrial node actually beats with a faster intrinsic frequency, so this is traditionally what we refer to as the heart pacemaker itself. The atrioventricular node normally has a slower frequency. Because of this delay in the conduction through the AV node, the signal is delayed in reaching the ventricles, so the ventricles will contract after the atria have finished their contraction cycle. In summary, you need to know the basic anatomy of the heart and how the blood circulates through it. We need to understand the cardiac cycle in terms of its mechanical events, so the contraction phases, how cardiac muscle is structured, and we also need to understand the cardiac cycle in terms of the electrical events of the ECG. The ECG is quite hard to get your head around. If you need additional help, please let me know.